All right. Seems like it's just us today in person, but Caleb and Alexis are watching digitally. I have the chat pulled up, guys, so if you have any questions, type it in there, and if I can notice it while I'm teaching, I'll try and address your question. Sound good? Give me like a okay in that chat room, and I would appreciate it. Just so I know if you're listening. Oh, I see a thumbs up. Apparently we have emojis in this thing. I see. Okay. All right. Good. So there's one more concept in the dot product section that we didn't get to, and that's called comp A B. This is called the component of B along A. And to understand what this equals, we have to talk about the projection one more time. The projection of B onto A. Recall that we derived that it equals this quantity, and that, remember, it's a vector. In my derivation, I had B here because of my vector B was the first vector we were talking about. It's no difference. Okay, so the comp A of B is actually just magnitude of this. So it's going to end up being just this value right here. Notice that when I take the dot product and divide it by magnitude squared, this is a scalar. Notice that this is a vector. So just know that this, this is equal to this, and projection is equal to this. Okay. So now we move on to section 9.4, cross product. Okay,
just like how the dot product, because at the end of it, we formed a scalar with the cross product, we can actually also call it the vector product, because once we take the cross product of two vectors A and B, that's why it's called a cross, because it's that X there, we are going to end up with a vector. It outputs a vector different from a dot B, which outputs a scalar. Okay. So this is sometimes called the scalar product or the dot product. This is sometimes called the cross product or the vector product. Okay. So let's talk about what it's defined as. A cross B is defined as being magnitude of A times the magnitude of B times the sine theta, where theta is the angle between the two vectors, times n hat, or n. And we could have called it n hat, but then we would confuse it with basis vectors, which both of them have something in common. Basis vectors and this n is a unit vector. It's a vector of unit length. But we want to have the basis vectors, I, j, and k, be distinct. So we'll leave the hat notation on them and let n just have its normal vector notation. N is a vector that sends the magnitude that's in here in a direction. So we talk about how A cross B creates a vector. Remember, what are the two things vectors have? Direction and magnitude. Perfect, perfect. So this is its magnitude portion, and this is its direction portion. This whole thing is the magnitude portion because it's just a number, and this part is the direction portion. Okay? Where theta is this angle between the two vectors. Now, one of the very interesting things about the dot product is that when it takes two vectors and it outputs another vector, and the interesting aspect of it is that it will output a vector that is mutually orthogonal to both the previous vectors. So this new vector that it outputs, A cross B, this vector will be mutually orthogonal to both A and B. If you can kind of imagine A and B being on the board and this A cross B coming out or going in, which brings us to another characterizing property distinct to the vector product or the cross product, is that we have to discuss the right-hand rule. Who here has heard about the right-hand rule? You saw in the book in the 9.1? Yeah. Have you heard about the right-hand rule? Have you guys taken physics? Physics 1, physics 2?
I took a little bit of physics.
Okay. We'll be talking about torque. You guys talked about the right-hand rule with torque, right? Okay. So this is how the right-hand rule works, all right? A cross B. Let me delete this. Let's start this all over again. A, B, angle between them. Okay. If I want to find A cross B as opposed to B cross A, let's talk about what that will form. Okay. To find where the vector gets created in the cross product, you have to use the right-hand rule. And here's how you do it. Everybody in person and everybody in home, pay very close attention to this hand. It's my right hand, okay? What you do is, the vector that's first on the left, you put your hand, arm, and fingers in that direction. So look, it's A, all right? Then you scoot your finger in the direction of the other vector. So, okay, right? You see that? Hand in the direction of the first vector, fingers point in the direction of the other vector that comes afterwards, B in this case. So we go, wherever your thumb is pointing on your right hand, that's where the vector is going. So that means my thumb is pointing into the board. See that? It's pointing into the board. So the vector A cross B will be going, it's really hard to draw that. It's going into the board. Sometimes they kind of draw like that for going into the board. Actually, sometimes they draw it like that, like it's the end of an arrow. So let's say you have an arrow, right? You know, the kind of arrow they used to hunt animals with and fight wars with. So whenever you look at this arrow from the back, it kind of looks like this, right? And whenever you look at the arrow on the not so nice end, you see the tip of the arrow and it's coming towards you. So sometimes this notation is used for vector is pointing out of the board and vector is pointing into the board. Okay, now let's talk about, now that we've figured out that A cross B is into the board, and you know what? Let's use our cool notation here. It's into the board. What is B cross A? Clearly, you kind of realize it's probably going to be one of the two, but you don't know which one. Let's use the right-hand rule again. Put your right hand and fingers and arm in the direction of the first vector in the cross product. In this case, it's B this time. So I go, okay. Then I must point my fingers in the direction of the second vector, A. So this doesn't count. I can't move my wrist to like point like that, right? So that's part of the rule. You can't move your wrist. Your fingers can only move downwards. They can't like go up, all right? That's the rules. If you follow these rules, it'll work. And this right-hand rule stuff will take some practice. B, since I can't go like this and I can't move my wrist, I have to rotate my hand to point it in the direction of A. Notice my thumb is now pointing out of the board towards you. So in this case, you get this one. All right. Now we've discussed the right-hand rule. Let us talk about torques. Typically, I denote torque with the Greek letter tau. What is torque? Does anybody in here know what torque is? You hear it on the car commercials, right? Like, this car has this much torque. You heard that before, right? Okay, so it has to do with cars, maybe. Does anybody know what torque has to do with it all? Did you talk about it in your physics classes? You don't remember what torque was about? Torque has to do with forces. So like I can impart a force out here, I can impart a torque. So a torque is a rotational force. It's a force about a fixed axis and arm that rotates about that. So like getting a wrench and tightening a screw, or a bolt, I mean, getting a wrench and tightening a bolt, actually a screw is a torque as well. But we're going to do wrench with the bolt. Screw is also torque because you're putting a rotational force onto the screw. So let's talk about a wrench and a bolt. Okay. Let's say we have some wrench and a bolt, and this is our R, our displacement vector from here to here. We could set up to have this be our origin, and we can create a displacement vector from here to here, okay, in 2D or 3-dimensional space, what have you. Let me now that's your bolt, okay? And we're gonna put a force from here, right? Force. This force is linear. We grab the handle from here, we push it down because we want to tighten it, right? All right, so that's the force there. Then what you're gonna get is, let me define what torque is, okay? To define torque, what is torque as a vector? I first define what is torque as a magnitude, okay? You know, I don't really have to do that. I can just define it right off the bat. So really, torque is R cross F. R cross F is the vector torque. You're taking the displacement vector, crossing it with the force vector to create a new vector, the torque vector, and that is like this. This torque vector comes out like that. So notice, how did I figure out that the torque vector is going into the board? Well, R, yeah, I'm on video. R, F, see my thumb? It's pointing into the board. So this is like going into the board. The torque is going into the board. Okay? And we have this thing, I'm going to shorten this a little bit, call this the torque. We have this thing called N again. N is a unit vector, and it points in the direction of the torque. Okay? So, by the definition we cited earlier, this must be magnitude of R, magnitude of F, the sine of the angle between the two vectors, okay? And don't forget this N, because all of that I wrote on the left until N is a number, and N makes it a vector. When you multiply that number, you scale the unit vector by that scalar quantity here. Again, in my notes I say here, notice the torque is only considered when the force is perpendicular to the lever arm. The lever arm is this thing that says R. This thing is called the lever arm. You know, they say pull the lever. What is a lever? It's like a pole or a rod, and you know, okay? I drive a stick shift car, and it has a lever. So you put the clutch down, you put in 1. So that's what levers are. There's something that you grab and you push and pull. Okay. Notice that what I'm saying here, the torque has to be, we only consider the force contributing to the torque, or the force components that contribute to the torque, that are perpendicular to the lever arm. What do I mean by that? What if you had this wrench situation and you push this way onto the wrench? Would that rotate the bolt? No. What if I grabbed the wrench and I pulled it? Would that rotate the bolt? No. Only pushing it up or pulling it down would rotate the bolt. So only those movements that are perpendicular to the lever arm will cause a torque, which will then screw the bolt in farther. Is that making sense? Okay. So that means if this force is not directly perpendicular, if it were somehow like this, notice that forces can be broken into components. This is some angle alpha. Notice that this right here would be F cosine of alpha, and this would be F sine of alpha. Okay, so over here, we would have to replace this with F cosine of alpha, because that's the only component of the force that is perpendicular to the lever arm. This component, you lose that force. If you're pulling on the lever in a weird way like that, you'll lose whatever force you're doing. It's better to put all your force into the vertical component to get it to rotate, because this F sine of theta is all lost. Okay, it's all lost force. You didn't really get any output out of it. The bolt didn't turn at all. Okay. Then clearly what I was trying to do is talk about what is the magnitude of the torque. It would just be this stuff. Where I could even replace that F with F perpendicular, or F component perpendicular. Okay? So it's got to be perpendicular to the lever arm, or else it doesn't produce any torque. Mathematically, that's due to the fact that if it's going like this, the angle between R and this F sine of theta component, they're both parallel. So the angle between those two vectors is 0. And so sine of 0 is what?
1.
That's cosine of 0. Yeah, sine of 0 is 0. And so that's why if I were to just pull on this, I wouldn't produce a torque, because sine of 0 is 0. And the same thing, that's why if I were to just push on this, there's no torque, because sine of pi is what? Yes, the sine of pi is 0. So even if I push it at 180 degrees like that, still we get 0. Okay? So speaking about 0, notice that if A or B is equal to 0, that implies A cross B will equal to the 0 vector. Oh, yeah. Because, let's say, for instance, A is the one that's equal to 0. You'd get that, right? But the magnitude of the 0 vector is what?
It doesn't have 0.
It's 0, correct. So this is 0. 0 times all this is 0. So you get 0 times this n, the directional giving vector, the unit vector. But whenever you multiply, whenever you scale that vector to 0, you get the 0 vector. Now, let's apply this problem to a real situation here. Let's say, again, we have this bolt. Got a wrench. Oh, well, I want the wrench to kind of be going up at an angle. Okay. Boom. My lever arm, because we start at the axis of rotation, and that's the center of the mass of the bolt. That's why we count that part too, because the rotation has to, you have to take into account where the center of mass is. So let's say we have a situation where this is like 0.25 meters. And let's say some not so good handyman, and I say this because they're pulling at a force of 40 newtons, but they're not really pulling on the wrench right. You see that? You guys see that? So they're grabbing the wrench and they're pulling sideways. Instead of pushing on it perpendicular, which would transfer all the force to the torque, they're doing some weird thing where they're pulling it sideways. Okay? So whatever torque that they wasted doesn't get added. Okay? So we notice that if I extend this out here, right, extend this out here, if this is 75 degrees and this forms a right angle, what is this angle? There we go. Okay, so keep that in mind there. Okay, so notice we can create this triangle where the magnitude of the force is equal to 40 newtons. This is at 15, right? This would make a right angle. So if that's at 15, right angle, what is this? What's this angle right here? 75. Yes. Mm-hmm. Also, that's just alternate interior angles. If you remember alternate interior angles. You guys remember alternate interior angles? Okay, that's what's going on there. But over here, this is what we would call the F sub Y, because it's in the vertical, okay? And this is what we would call the F sub X, because it's in the horizontal, okay? So, at this point, what really matters is what is the angle between the lever arm and the force. Which one is it? The 15 or the 75? It's kind of tricky, so I won't wait too long to hear your answer. It's actually 75, even though it looks like 15. Right? It looks like this is the angle between them. But no, the angle between them is 75 because that's how much deviates from the straight path. If that makes sense. 15 is not how much it deviates from this straight path. It's, if I were to extend this lever arm out straight, and if this vector goes this way, we measure this quantity as the angle between them. So torque is equal to R cross F. And we figured out that this is magnitude of R, magnitude of F, sine of the angle between them. So we have everything we want. And this is 0.25 meters. This is 40 newtons. And this is sine of, we've discovered, 75 degrees. Okay. So we get, when we do the calculation, the torque is equal to 9.66, the magnitude of the torque is equal to 9.66 Newton meters. And what about the torque vector? Well, we got to use that n to send it in the right direction. So say that the vector torque is 9.66 n. And where does n point? N points in the direction of the torque. And where does the torque point? How do we determine where the torque points? The what hand rule? Right hand rule. So it's R cross F. So the torque is going into the board. Okay? And thus, so is N. N is going into the board. And it is mutually perpendicular to these two angles. You can think of those angles, you can think of all this being in the plane and torque going into the board. Now let's talk about the cross product on unit vectors. So recall our basis vectors. Here's X, here's Y, here's Z. Here's my I hat, J hat, K hat. There are basis vectors. Basis vectors are vectors of unit length that point in X, Y, and Z directions. Remember, you can component-wise define them as so. I put 3 lines because they're defined to be that. They are equal that, but they're also defined to be that. So okay. What is, let's say, I cross J? Huh? By the definition of the cross product, it's this. Well, what's the magnitude of I? Yes. What's the magnitude of J? Okay. Let me write that down. 1. What's the angle between them? This is I, this is J. 90. What's the sine of 90? Yes. So we get then. So where is n pointing? What hand rule do we got to use? Right hand rule. Which vector comes first, I or J? I. So hand in the direction of I. Okay. My fingers have to go this way for J. Notice that it seems like it's coming out of the board. That means it's going through the z-axis. So what is N? What is a unit vector that points in the z-axis? Yes, k hat. So this equals just k hat. Because all the ones are trivial. They're just multiplying ones. Okay? Now, will something change if we change the order? Let's see. By definition, this is magnitude of j, magnitude of I, sine theta, n. What's the magnitude of j? What's the magnitude of I? What's the angle between them? This is just 1 times 1 times 1 times n. Oh, well, they're the same then, right? Oh, this young man is saying no. Why? J comes first. So the right-hand rule is different, right? Okay. Let's see. J cross I, okay, versus I cross J out. J cross I in. You see that? So if the mutually perpendicular axis on the first one was the z-axis, it has to be the z-axis here again, right? So shouldn't it equal k hat? Aha! It's going in the opposite direction as before, right? Oh, so it's not just k hat. It is negative k hat. Right? Aha! So, in general, we say that the cross product is a non-commutative product. That means A cross B does not equal B cross A. But this is true. A cross B does equal negative B cross A. So, now let's talk about the cross product axioms. This allows us to segue into the cross product axioms. One that we just discovered earlier. The fact that scalars can scale the first vector, then cross, then scale, or scale the second vector, then cross. They're all the same. This shows you how vector addition interacts with the cross product. It interacts very interestingly by distributing. the cross product distributed to the sum. Very interesting. And what about this situation? Because we realized that being on the left or the right does matter in cross products. In dot products, it didn't seem like it mattered. But in cross products, it doesn't matter. Actually, no. I aspire to put some YouTube proofs on these guys right here. But for now, you could just take them as given. A very interesting observation about the cross product. Let's say you have two vectors like so. Even with this mask, I'm always breathing in chalk.
How many times do you go through a day?
At least one. Sometimes more. If I'm working outside and stuff like that. And it's really hot. But yeah, I don't really feel good unless I drink a lot of water. This one time, I had a lot of caffeine, not a lot of sleep, not a lot of water, and I had to go to the hospital. Yeah, for dehydration.
You drink caffeine a lot, like regularly?
Well, I was studying a lot and a lot of very difficult courses, and let's say I wasn't managing my time wisely, so I was trying to utilize caffeine to make more out of the small amount of time that I had. And so yeah, caffeine is a very great tool, but just like every tool, if you abuse it, it can lead to damage. Like with the wrench. Use the wrench to tighten bolts, wonderful. Use the wrench to hit it on your head, not wonderful. It's going to hurt. It's going to cause damage. So every tool is useful within its own like uses. You can't overdo the caffeine either, okay? I'm a really extreme kind of person, so I have to learn to modulate and regulate and be less extreme with certain things. So after that situation, I told myself, you got to carry a jug of water and eat it, or not eat it, but drink it every day. Drink a lot of water. Plus, I sweat a lot due to strenuous physical activities, so that helps with that. Let's talk about how the cross product relates to the area of a parallelogram. Interestingly enough, it relates to the area of a parallelogram. Okay, this value here is magnitude of b sine of theta. That's, I mean, I don't have to do it for you guys because you guys are good at trig, but I'll do it real quickly. Notice that sine of theta would be, if this is y, this is x, would be y over magnitude of beta. And so this height y, when we solve for it, it's the same thing as magnitude of, did I say beta? I meant b. Magnitude of the vector b sine of theta is equal to y. That's why we put that here, because this y here and this y here are the same. It's from trigonometry, simple application of sine to this angle. So notice we have that parallelogram. Who here can tell me what the area of a parallelogram is?
Base times height.
Base times height. Okay. If that's the case, then the area of this parallelogram would be base, magnitude of the vector A, right? Times height, times height, right? Oh, wow. What does that equal? It equals the magnitude of this, doesn't it? Because, I have to take the magnitude, because the magnitude part is equal to this. The vector has that n. Can you guys see that on the video? So the magnitude is just everything but the n. So interestingly enough, the magnitude of the cross product is the area of a parallelogram generated by the vectors here. That is quite astonishing. You wouldn't just kind of guess that out of nowhere. I wouldn't expect that to happen, because, what is the cross product? A cross product creates a vector that's mutually perpendicular to the two vectors that points out depending on the right-hand rule. How in the world does that relate to an area? It creates a vector. How does that relate to an area? Area is a number that quantifies how much space is located within a confined region of lines or curves. How does that relate? How does the magnitude of that vector relate to the area? It's quite astonishing. Quite astonishing. It is an astonishing result, and I find it very interesting. So does your book, and that's why it talks about it. But know that one of the cool, interesting properties of the cross product is that it allows you to calculate the area of this parallelogram that you can generate. Now, moving on, remember how the dot product had a component-wise characterization? Well, guess what? So does the cross product. Remember that? Remember that? Yeah, okay. So, what does it equal in terms of the components? This is going to take some calculating, okay? So, notice that I can represent A cross B as A1 I hat plus A2 J hat plus A3 K hat. Board space usage. A cross B. I'm just rewriting it. This is A1 I hat plus A2 J hat plus A3 K hat cross B1 I hat plus B2 J hat plus B3 K hat. Okay. Now I'm going to take their cross product. If you recall the axioms that I erased, the cross product distributes across addition. So I'm going to call this whole thing is A, right? This whole thing is A. I'm going to have A distribute to each of these just to save notational space. So this is A cross B1 I hat plus A cross B2 J hat plus A cross B3 K hat. All right. Next, notice that really this B1, B2, and B3 are hanging out with this IJ and K. We don't really want that. We want to use another one of the vector axioms to create this situation. Now, I will call this A, this term. I'll call this term B. I'll call this term C. And that is the same thing as A plus B plus C. What we're trying to find, the cross product component-wise definition of A cross B is the same thing as A plus B plus C. If this is like alarming you, this is not going to be, this derivation is not going to be on your test. This is just for your information. So just enjoy the ride. Enjoy the derivation. And by all means, just because it's not on the test, that doesn't mean you shouldn't try and understand it. Try and understand it because it will make you understand what's going on a more deep level. Okay, so let's discuss what A ends up becoming. A is this piece right here. So now I'm going to break apart the vector A. So this is B1 times the vector A, A1 I hat plus A2 J hat plus A3 K hat cross I hat. Recall, the cross product distributes across addition. So I get A1 I hat cross I hat plus A2 J hat cross I hat plus A3 K hat cross I hat, all multiplied times just B1. You guys see that? Cool. Yes, I like how you guys are now sitting back and just watching, because not only do you get the video, something that was unheard of until these recent times, but just writing stuff down, you can't really follow. You're too busy writing. Okay, sit back and relax. Okay, sit back and enjoy. Really. What is I hat cross I hat? Well, no. I hat cross I hat says, what is the magnitude of I? 1. Times what is the magnitude of I? 1. Times what is the angle between I and itself? Yeah. So what is the sine of 0? So what is 0 times 1 times 1? So the whole thing is, so this all goes to 0. But these two don't necessarily go to 0. Okay? What do they go to? Well, you got to do the right-hand rule, remember? So J points in the Y, then we got I, so it's pointing into the board. So this would be like a negative K hat. And what about this? K, I, what is this? Positive what? J hat. Okay? For the sake of time, I won't go through all of it. I won't go through all the steps, but you do something like this to the A term, the B term, the C term, A term, B term, C term, okay? To prove all of it would take 30 minutes, but I wanted to show you how it's like working, how it's set up. Okay? That's how it's set up. Once you do all of those steps for A, B, and C, you get A cross B reduces to this A2 B3 minus A3 B2 all times I hat plus A3 B1 minus A1 B3 all times J hat plus A1 B2 minus A2 B1 K hat. Or, in my favorite bracket notation, A2 B3 minus A3 B2, comma, A3 B1 minus A1 B3, comma, A1 B2 minus A2 B1, bracket. So this is all you're gonna have to remember to do. You'll be given a vector with like components. Like, let's say A is equal to 1, 2, 3. B is equal to 0, 0, 1. And you'll have to do this right here. So A cross B will create this vector. A2, this is a 2, B3 times 1 minus A3, that's a 3, times B2, that's a 0, comma. And then you just do that. You see what I'm saying? That's how you can just do the cross product with the components really easily. Let's see, what time is this class over? 8:50. 8:50? Well, it's 8:54. Huh? Okay. I'm gonna have to stop. Your homework for this section will be posted online. I'm glad that I don't spend time doing that anymore, so that we can spend time more on the deep mathematics.